Acha, if you can't recollect, then I'll explain that again. Perhaps a recap is in place. We had learned two hypotheses for the formation of the gas giants. One was the core accretion model and the other was the disk instability model, right? One says that the rocky and icy cores, they form first and then through gravitational attraction, right, these planetesimals, they acquired a gaseous envelope of volatile material. So basically, after the formation of the sun, the first objects to form in the solar system were the gas giants, starting with Jupiter, right? The other is the disk instability model, that just like the collapse of the molecular cloud in the first stage over here, there were swirls being produced and there were many versions of sun formation happening. So that did not require the core to accrete first. Okay, so basically the gas giants, they have formed the rocky planetesimals, they start to acquire a gaseous envelope, right? All this happened within the first few million years of sun formation, stellar formation, right? And that led to a lot of bodies that were present over here. Then we learned two growth stages. ये कौन बताएगा? Manav, two main stages of planet, formation.
Uh, I can't remember exactly, I guess. I can't remember that exactly, sorry.
Okay, no, that is okay. The runaway growth stage and the oligarchy growth stage. In the runaway growth stage, small bodies, they grew very rapidly from, few millimeters to few centimeters, few kilometers to few thousands of kilometer size, basically moon-sized bodies, right? And basically the number of bodies were decreasing. If you see the disk of gas and dust was very crowded over here. At each stage, it is getting cleaner. It is getting swept off of material because all the material is accreting to form larger bodies, right? So that was the runaway growth stage. Number of bodies is decreasing, but the size is increasing, and the larger bodies tend to get even larger, right? Gravitational focusing, dynamical friction, these were the main factors that played a role over here. And that was followed by oligarchic growth, impact related growth, right? When Mars sized planetesimals, they started to grow, right? And finally, we arrive at, with the planetary system of the sun in about 30 to 100 million years with all the differentiated planets, right? And then we spoke about different heat sources, how the planetary bodies differentiated. Because if you look at the first stage, the material would have been fairly homogenized, as also evident from the presence of the chondritic meteorites. And then finally, we arrive at these differentiated planetary bodies. Okay, one thing that we are here to learn. There has to be a takeaway, so sab log participate kare. I think that would be wonderful, right? And if you can't recollect anything, that is fine. We'll do a recap. Please try to participate. Okay, so let's move on to the architecture. So I am going to email you the glossary, right, to familiarize you with some of the concepts. It's almost done. Just the last bit I had to add about some of the comets. I'll do that and email that to you today, right? Just browse through the glossary. Okay, to familiarize yourself with the general terms. So here the main objective is to understand the location, nature, origin of the small bodies within the solar system. Until now, we dealt with the larger planets, right? We'll again go back to them, their interior structure, experimental part, behavior of material under extreme conditions. But before that, let's know a little bit about the small bodies present within the solar system. So we are going to be covering comets, the Oort cloud, Kuiper belt, right, trans-Neptunian objects, asteroids, near-Earth objects, meteorites, micrometeorites, cosmic spherules, right, where do we find them? What is the significance of understanding these smaller bodies in the solar system, right? So the rocky or terrestrial bodies, basically, these small planets near the sun, you can see the relative sizes compared to the larger planets here, right, are located near to the sun. Gas giants are located further to the sun. In addition to the major planets, right, and many of these planets have their own natural satellites, their own moons. There are innumerable smaller objects, minor bodies, which occupy some of the regions between the planets, right? The interplanetary regions, for example, the asteroids, which are mainly found in the asteroid belt between Jupiter and Mars, somewhere over here, right? And there are also regions beyond the planets, right? Beyond the orbit of Neptune, right? That lots of, small minor bodies are present over there, comets that are found in the Kuiper's belt, right? And the Oort cloud, both situated much beyond Neptune. So we are going to be studying about these objects. So in addition to the larger, the minor objects that I just mentioned, the comets, the asteroids, there is also abundant dust that comes from a variety of sources. And this dust that bears very important information about, some of the early planet formation processes, as well as the material that was incorporated into these growing planets, right? And what are the kind of processes that are still going in the solar system. For example, the dust trails of comets, right? From the collision of asteroids, the dust that is originated somehow, if we can get access to, that sheds a lot of information on these processes. So this lecture, plus more in the course, we'll be investigating some of these smaller bodies, which is going to give us important insights into the processes that formed and modified the solar system and are still modifying the solar system. So basically, starting with the comets, right? If you look on the right hand side, there's a picture, right, of the comet Hale-Bopp, and that was taken in 1995, discovered by Alan Hale and Thomas Bob, right? So basically, a comet is a body which is much smaller than a planet, much smaller. Okay, it contains a significant fraction of ices, basically volatile material. When I say ice over here, right, it's not just water ice, but it could be ammonia ice, methane ice, right? And so these are volatile rich bodies that orbit the sun. And once a comet has been discovered and confirmed, it is announced by an international body known as the International Astronomical Union, right? Once its presence is confirmed. So the nomenclature, how comets are named, it's actually quite complex, right? But in general, comets are designated by the years of discovery, right? When they were discovered, by the name of their discoverer, right? For example, this comet called C/1995-01, right, or the Hale-Bopp comet, by the name of their discoverers, right? And 1995, that is the year of the discovery, and they are, subdivided into different categories. That is why these prefixes, right? So again, this picture on the top that shows different stages of a comet, that here is a volatile body orbiting around the sun, right? And that's the orbit that this, volatile body is, forming around the sun. The sun is depicted by this yellow blob over here. And at a point of its closest approach or in near vicinity to the sun, what will happen? Because of the thermal gradient present in the solar system, the ice or the volatile material will start to volatilize, right? So while the comet is in the near vicinity of the sun, it will leave off like a trail of volatile material, which we see, or we at times we can observe in the form of this dust and gas tail, right? And here's a sodium tail, because sodium, potassium, these are very alkali metals, but these are very volatile. They would, move on into the gaseous stage at relatively lower temperatures compared to other elements such as calcium, scandium, aluminium. And by their spectral analysis, we know that this comet, when it was near the sun, it was leaving out a tail of, predominantly sodium. So some comets are also named after the observatory that first discovers them. For example, Linear Soho, we'll talk more about this. The periodic comets such as the 1P or the Halley comet, Halley's comet, they do not have years of discovery, right? Because they would have been very volatile rich, going on through, way back, and documented only in recent history or a few hundreds of years back. So we don't know that which year they were discovered. The prefixes before the year of discovery are important indicators, like I said, of the type of comet that we are dealing with. For example, C over here, or at times there are prefixes like P, right? And we'll see what that means actually. So P, that indicates a periodic comet whose periodicity is established. C, prefix, that indicates a non-periodic comet. And again, I would request you that don't worry about memorizing this stuff. Most of the material or all of the material I'm going to be sharing with you. right? The prefix X that indicates a comet for which no reliable orbit could be calculated. And generally, these are historical comets that somewhere we find instance, of their or reports of their occurrence. But right now, we don't know, what's their orbit like. And when we'll deal with the Oort cloud, you'll understand why I'm saying that their orbital period around the sun, right, may actually overlast several, not just hundreds, but many more years. So we don't know. There's no reliable orbit that could be constructed for these. So that is why these prefixes. And the prefix capital D that indicates a defunct comet. Right from the name where I say defunct means dysfunctional comet, a comet that has lost out on its volatile component. Right. And if you remember, when we defined a comet, it was mainly on the basis of the icy or the volatile component. Right. So the prefix A that indicates an object that was mistakenly identified as a comet, but is actually a minor planet or a small asteroid, right? So we take into account all these things as well. However, the formal IAU definition of a comet that requires that it shows cometary activity, right? Basically leaving out a trail of volatile material in the region where it closely approaches the sun. Basically, the ice sublimates, volatilizes, and the comet develops a tail or a comma. The comma that we use while writing in the English script, right? So comma means basically a full stop with a tail, right? So that is just to illustrate the point, right? A comet has to show cometary activity leaving out a tail of volatile material, which only happens when a comet approaches the sun. So although this is not a very quantitative or a useful definition when trying to distinguish between comets and asteroids, but on the basis of the IAU definition, a comet has to show cometary activity, and once it stops to show cometary activity, it is termed as a defunct comet, right? So many comets, called the long period comets, have orbital periods greatly in the excess of 200 years and orbital inclinations that are randomly distributed. Right. So if you look at this picture on the right hand side, right here, right in the middle, we have the sun, right, shown by this is small, I don't know how clear that is, but this is small yellow bleb very here, and surrounded by this kind of bubble over here, right? And that bubble, the locus of all these points together, right, it's like a bubble engulfing the solar system much beyond the object of Neptune. Okay. And that's the origin of many of these cometary bodies. So they are therefore sourced from a spherical cloud of bodies in the far out reaches of the solar system. And this, imaginary bubble, which is the source region, right? We cannot observe this bubble. That is why I'm saying imaginary. But on the basis of reconstruction of the orbits of all these long period comets, right, it appears that there's a bubble of volatile material that is surrounding the solar system. And that is the origin of many of these long period comets over here, right? So, and that bubble is called the Oort cloud. Okay. And the Estonian astronomer Ernest Oppik, he way back, almost 100 years back, he suggested that a huge but very distant spherical cloud of comets surrounds the solar system. At that time, he didn't have much quantitative evidence for that, and the idea was later developed by Jan Oort, and the cloud became generally known as the Oort cloud, right? Or the Oppik Oort cloud. So again, here is a schematic of this. If you look, bring your attention to the top figure over here. Here we have the sun in the center, this yellow bleb. These are the orbits of the different planetary bodies. Neptune's orbit, then Pluto's orbit, right? And finally, we have the orbit of the binary Kuiper belt, and much beyond that, we have the orbit, of the we have the presence of this bubble kind of a structure, very distant spherical cloud of comets that is much beyond the orbit of Pluto, right, which covers the entire solar system. And the Oort cloud basically comprises of many, many billions of comets. The total mass of this is actually comparable to the mass of one of the much, much smaller bodies in the solar system, but the amount of, material that is dispersed over a very large surface area. Okay. So, like I said, we cannot directly observe the Oort cloud, but we infer its presence, or its presence was, constructed from the reconstruction of the orbits of the very long period comets whose orbital periods exceed about 200, you know, years. So now I've just tried to see the size comparison here. We have the sun in the center, and that's basically the Oort cloud engulfing the entire solar system, right? And calculations, they suggest that there may be, actually, I think this is 10 to the power 12 and 10 to the power 13, actually. Okay, so that's not 1012. Sorry about that, I'll correct that. So there may be 10 to the power 12 to 10 to the power 13 comets in the Oort cloud at the present times in a shell which lies about, 103 astronomical units to 105 astronomical units from the sun. So those are the kind of distances at which the Oort cloud is present and the number of bodies that are present in the Oort cloud. So this sounds like a very large number of comets, but it's basically a small amount of material that is distributed over a very large surface area. And each individual comet is very small, has got low density, largely consisting of volatile material. And the total mass of all the comets in the Oort cloud is only, just about the mass of the Earth. Okay. So it's commonly thought that the Oort cloud was formed from icy planetesimals or volatile material that were left over from the formation of the solar system, right? Material that was thrown out from the inner part of the solar system by the gravitational effect of the larger gas giants, basically Jupiter and Saturn, right? Thrown towards the outer periphery of the solar system. Now, what are these comets actually made up of? So, from whatever spectral analysis we have of the cometary tails and other constraints, we believe that most of these are made up of various kinds of ices: methane ice, water ice, other organic material ice, ethane, carbon monoxide, hydrogen cyanide. So basically made up of carbon, hydrogen, nitrogen, so molecules made up of these elements, which are the volatile elements. And we believe that these are the predecessors of comet compositions. And many of the icy bodies would have been lost from the solar system, completely escaping the solar system, but a small portion was retained within the gravitational attraction of the sun that we now have access to in the form of these cometary bodies. Right. So we learned about the long period comets whose orbital periods exceed 200 years. Then there's a second group of comets termed as short period comets because their orbital periods, are less than 200 years, right? And we believe they cannot be derived from the Oort cloud because of their orbital inclinations, mainly less than 35 degrees. Because while we construct, their revolutionary period, right, around the sun, we also construct their orbits, what's the inclination, whether they have a regular orbit, right? So these objects whose, periodicity orbital periods are less than 200 years, they all seem to come from the same place, right? And their orbital inclinations are mainly less than 35 degrees. So there has to be a second source for these comets within the solar system, and the existence of a belt of comets beyond the orbit of Neptune, right, between 34 and 45 astronomical units from the sun, that was proposed by both Edgeworth and Kuiper. And so this entire belt is named after them. It is known either as the EK or the Edgeworth-Kuiper belt, or sometimes just as the Kuiper belt, which is just beyond the orbit of Neptune with a slightly inclined orbital, inclination, less than 35 degrees. So there are two main sources of comets. One is the Oort cloud, completely, engulfing the solar system towards the outer periphery, situated at a distance of almost 104, 105 astronomical units from the sun, right? Very, thin cloud of material. And the other source of the comets lies in the Kuiper's belt or the Edgeworth-Kuiper belt beyond the orbit of Neptune. Okay, which are these short period comets. There are several further subdivisions, like I mentioned, right? There are prefixes attached, but these are two major subdivision of comets into short period comets and long period comets. Okay, so let's talk about the Kuiper belt. Bodies in the Kuiper belt, some of them are large enough to be visible from Earth-based telescopes, and also the Hubble Space Telescope, which used to be a very useful, tool. And bodies as small as about 200 kilometers across have also been discovered in the Kuiper belt, right? So if you remember Pluto, poor Pluto, which used to be a planet, right, way back, but now considered to be one of the largest bodies in the Kuiper belt, having been downgraded from the status of a planet to a dwarf planet, right, by the International Astronomical Union. And again, these bodies are thought to be a mixture of ice and rock, and they are believed to represent, leftover planetesimals that formed at the start of the solar system. And somehow, these nucleus, they could not grow into full-fledged, planetary bodies. So that is why they hold very important, information about the early stages of planetary evolution. And just, as a, interesting fact, that there are several, scientists who are still pitching for Pluto to be upgraded back to the status of a planet, but that we'll deal with in one of our tutorials, right? That what makes a planet and what, are the basic requirements that a planetary body qualifies as a planet, and what are some of those properties that Pluto doesn't have. That is why it was downgraded from being a planet to a dwarf planet, right? So that could be either be a good topic for a micro presentation by one of you, or I'll deal with this in one of the tutorial lectures, right? So here's a picture that shows many of these minor bodies, right? Trans-Neptunian bodies and the relative sizes with respect to each other and to the Earth. For example, here we have Eris, Sedna, right? Pluto has its own moon, Charon, right? Makemake, right? Haumea, Varuna, right? Some of these, they derive their names from different, cultures across the Earth, right? So these two names, Makemake and Haumea, they come from the Hawaii Islands. Varuna, that's a Sanskrit word, right? So many of these objects are named like that. And here we have the Earth over here. So you can compare the size of these objects. Many of them are just several hundreds to few tens of kilometers across. And you see even there's some of these natural satellites around these bodies, right? They have their own natural satellites. They're even much, much smaller. So all objects in the Oort cloud and the Kuiper belt, together with the scattered disk objects, are collectively known as trans-Neptunian objects that are present beyond the orbit of Neptune. Pluto was the first TNO to be discovered in 1930. Right, most of these bodies used to be given a provisional name first and later on full-fledged names. Right. The largest TNOs are mainly found in the Kuiper belt, and they can attain the status of a dwarf planet. For example, Pluto and Eris both have diameters more than 200 kilometers, right, across 2000 kilometers across. Okay, so these are some of the larger bodies in the Kuiper belt. And then there are several smaller bodies which are just tens of kilometers, almost the size of a small town on Earth. I'll show you some of those examples as well, right? So let's talk about asteroids and near-Earth objects. Right, we learned about comets. So who is going to, just a quick question. So let us see. I'll start with Gopal. Can you hear me? What defines a comet? What is the main property of a comet or a planetary body to be defined as a comet? Who is going to answer that question? Gopal, Manav, Mohak, Rishika, Saksham, Saurabh, Shubham, Siddharth.
I guess the main defining characteristics to be required is that it should be made up of icy and volatile material, and for it to be a comet, like it requires to have a tail when it comes near the sun. It orbits near the sun.
Exactly. Very good. Manav, it has to show cometary activity, right? So that is how a comet is defined. Then the other minor, objects in the solar system are our asteroids. So asteroids are basically rocky, can be rocky, made up of rocky material, or made up of carbon-rich, carbonaceous material, or even made up of completely of metal. I'll show you the example of an asteroid called Psyche, right, in which we are very much interested because it's made up of largely of iron metal, and potentially it contains a lot of, these platinum group of elements. So the European Space Agency or NASA is very much interested in that. They even wanted a couple of years back that if a certain portion could be scooped out and brought to the Earth, or somehow we can, bring that small metallic asteroid to the Earth. So still the plans are going on. So an asteroid can be either a rocky, carbonaceous, or metallic body, which is basically much, much smaller than a planet, and of course orbiting the sun. So most of the asteroids are in semi-stable, low inclination orbits between, present between Mars and Jupiter, the asteroid belt, right? So here there are two pictures. So these are the first close-up images of asteroids Gaspra and Ida. This is Gaspra and this is Ida. So you can see these are basically potato-shaped objects, right? Irregular shaped objects, right? These images were obtained by the Galileo spacecraft way back in 91, 93, right? Gaspra, the dimensions are basically 18 into 11 into 9 kilometers, right? Ida is slightly larger, 55 into 24 into 20 kilometers. Okay, so basically the size of a small town, right? So that's the size of these asteroids. And if you look carefully in this picture over here, can you see a second object, the right hand side here? So basically, IDA has even a small satellites of its own, which is visible towards the right hand side over here, named Dactyl, right? Whose dimensions are 1.6 into 1.4 into 1.2 kilometers, right? So which orbits about 100 kilometers away from IDA. So you see, they're very, very interesting objects out there in the solar system. And of course, there are many, many asteroids that have been closely studied or pictures taken in the recent years, right? Asteroids are Pallas and Vesta. They are now considered to be examples of surviving planetary embryos. Here are some close-up images of these, right? So if you see, this looks like, again, like a potato-shaped object with lots of these, dents on the surface. Any guesses? What is the reason for these dents on the surface?
Craters.
Yes, craters. And how did the craters formed?
Asteroid impacts.
Because of impact of smaller bodies when these bodies were still forming. So what does that tell us about the early history of the solar system? It was not a very nice place to be in, right? Quite a violent place where lots of collisions happening, right? And these surviving planetary embryos, right? They have evidence of that. And that also tells us that when the Earth or Earth-like planets were growing in size, they would also have suffered a lot of these impact processes, right? The Pallas and Vesta are now considered to be examples of surviving planetary embryos. About Vesta, we'll learn in much, much more detail later on, because it is not just a surviving planetary embryo, but it was visited by NASA's Dawn mission a few years back, and spectral analysis were taken of the entire surface of Vesta, and we also have rocks from the surface of Vesta in the form of HED meteorites. So we have samples from Vesta. A spacecraft has visited Vesta, and Vesta has a very Earth-like structure, although not an Earth-like shape. It's irregular shape, but it has got an internal structure similar to the Earth. So it makes a very important, case study if you want to understand planetary formation processes. Right. So the largest main belt asteroid series was also recently reclassified by the IAU as a dwarf planet. So here, if you look at this picture on the left-hand side, again, lots of craters on the surface, right? But what makes it very important was the detection of carbonates, right? On, if we detect, these kind of material on other planetary bodies, that tells us about the presence of volatiles, right? Or even the presence of liquid waters. So how is carbonate linked with liquid water? Anyone? what is the connection between, the presence of liquid water and carbonates?
Sir, due to long standing of water, the minerals rising from the rocks below the surface of the water, they get converted into compounds like gypsum.
And basically, these species like carbonates, sulfates, they get dissolved in water, and when the water would evaporate, right, these minerals are going to crystallize. So these are evaporite minerals, right? They form out of crystal, when water gets evaporated, they form as evaporite minerals. So if we find the presence of carbonate somewhere, that could be an indirect indicator that at some point, liquid water that had got dissolved carbonate was present on that planetary body. Okay, so the detection of carbonates on other planetary bodies is assumed to be an indirect evidence that liquid water was once present over there. And on Ceres, the presence of magnesium carbonate, sodium carbonate that was detected, right? So which was lot unexpected and was considered to be a very big discovery at that time, because if Ceres was nothing more than a long, defunct or dead ball of rock, then these compounds would have evaporated over the past tens of millions of years. So that means that either something is still happening in the inside, there's still some heat preserved, there's still some volatiles that are present over there, or else during its, thermochemical evolution, the volatile material basically volatilized, got lost, but these evaporite minerals are still present on the surface, right? So again, that is something very important that as planetary scientists, we are on the lookout. And if some of you were following the news, few years back, it was a very important discovery that on the surface of Mars, some of these evaporite mineral deposits were found, which were, their volume was changing, that they were being observed over an entire, Martian year, right? And it was found that their volume was changing. So what was thought that the volume of these evaporite minerals was changing because there was subsurface water present below the surface of Mars, right? And as it was approaching near the sun, the water was getting converted into liquid water. And as it was moving away from the sun during its orbit, right, orbital period around the sun, in that case, it was again solidifying. So again, there are follow-up studies that are going on. Mars rovers is sending, quite a lot of important data, but that is something as, planetary scientists, we are always on the lookout for, because the presence of liquid water makes the Earth so unique. So there has to be, a possibility that other planetary bodies, either they still contain subsurface water or they contain water at some point during their evolutionary history, right? So talking about asteroids, okay, that our asteroids named, how they were discovered. So they were originally named after Greek or Roman, gods and goddesses, but now formally named by the International Astronomical Union. And they are given numbers in order of their discovery and names of very prominent people, right? For example, here are some of the names: 1697 Saksham, 1725 Shubham, right? Well, that's a joke, but actually, this one, the 8356 Vadhva asteroid, that's named after Meenakshi Vadhva, who is one of the very prominent planetary scientists. The other names I have taken from you guys, but there's potential, of course, just to illustrate the point that the name of the discoverer or the names of very prominent people. So one of these asteroid was named after Meenakshi Vadhva. She's, I think, the main planetary scientist at the Arizona State University, also the curator of the Natural History Museum, right? And she did her initial studies in India, but then went on to the US for a PhD, and one of the very big names among the planetary scientists. And she has an entire asteroid named after her called 8356 Vadhva, right? So these are some of the ways in which asteroids were named. Okay, so a quick subdivision. Our asteroids divided. They are divided into different groups depending on their orbits within the solar system, their reflectance spectra, right? Basically their chemistry. So if you look on this cartoon on the right hand side, here we have the sun, then we have the orbit of the different planetary bodies, then here between Mars and Jupiter we have the asteroid belt. So the basis of the subdivision of asteroid into different groups is basically their orbits within the solar system and their chemistry, basically their reflectance spectra, because we don't have access to samples from all of these, but we do have access to spectra, right? Spectral analysis can be done on the basis of spacecraft data, even telescopic data, right? Which tells us about the mineralogy, what kind of minerals, what kind of, chemistry is present on the asteroidal surface, right? From which at least 13 different kinds of asteroids have been identified. Now, automated surveys of asteroids, use of neural nets that may extend the total number of classified asteroids from several thousand to about 20,000 in the near future. Right, so what I'll do, I'll be stopping over here and then we'll meet again next Tuesday, right? And those of you who actually, participated in the class, thank you. And let's meet again on Tuesday. And if there are, any questions, queries, any interesting information, please feel free to share, speak up during the class, because that is how we can make the class more interesting. Otherwise, it basically becomes like a monologue, right? Can you guys hear me? Yes, please.
Sir, I had a doubt. Why do the dust tails and gas tails from a comet separate out like
Okay.
as
So
you had shown in the picture?
yeah. So many of these comets, they are made up of very friable material, right? They are not consolidated so much. They are just held together. Let us say in the laboratory, if you take, very fine mixture of small amounts of dust together with large amount of ice, right? You just put it in the freezer. Okay. You form an ice cube, which has got very small amount of dust particles in it, but large amounts of volatile. And here the volatile is, in case of comet, it is not just water ice, but it could be, like I said, ammonia, methane, different kind of volatile species, right, together with some amount of rocky material. So as these objects are, and they are very friable in nature, okay, they are loosely consolidated. So when they start to approach near the sun, the heat from the sun starts to volatilize or evaporate this material, which as they are moving swiftly around the sun, which looks like, because they are in motion, that there is a tail that is being left behind. So basically that is just the loss of material. Okay, so that is observed in the form of a tail. And they are, and not just, these volatiles, like I mentioned, made up of carbon, nitrogen, hydrogen, but also there are volatile elements. If some of you have done chemistry practicals with sodium, right, in its metallic form, if you remember, it used to be very volatile, right? So in the same way, sodium and potassium, they are also lost very rapidly the moment the heat rises to few hundred degrees, right? At the point of, in the region of closest approach to the sun. So all these things are expunged first. And if the comet survives, it moves away, right? And then it again crosses, near the sun. It would lose out on its more material. But that is why we see the coma-like material, because of the loss of the volatiles. So that is why a cometary activity, right? Because when it was first observed, it was found that, there's a body moving with a trail of material behind it, like a tail, right? So it's because of that the term cometary activity or comet came off, like a comma. It leaves a tail behind that. Basically just lost of volatile material because of the heat from the sun. And as it is moving, yes, exactly. If you remember, we had, when we were dealing with, the cometary nomenclature, I had shown you that there are comets known as the defunct comets, right? With a capital D, the comet which has lost out on its volatile material. So that leads to a very interesting question, that once a comet has, has got done with its cometary activity, lost out on all volatiles, would that still be a comet, or would that be considered something else? So that is an open question that I'll show you that, sometimes there's confusion whether to classify a body as an asteroid or a comet, right? Because a comet that has lost out on all its volatile just contains some refractory material, so that won't show any cometary activity, right? So it basically is termed as a defunct comet, non-functional comet. So anyone
Hello, sir.
else? Yes, please.
Sir, actually, my question was, can you go back to the slide where the comet was orbiting the sun?
This one.
Yes, sir. See,
Yes.
the gas tail and dust tail are differentiated. Why is that?
Okay, so the gas tail is basically made of volatile material, and at times the dust tail, like showed you this example over here, the sodium tail, it's made up of, non-volatile elements other than the, carbon, hydrogen, nitrogen, right, which form the volatile ices. There is also some solid material, like I said, right, made up of rocky material. So that is why we differentiate between the gas tail and the dust tail. The gas tail is predominantly made up of organic materials, and the dust tail is made up of inorganic material, right? Basically of solid particles that are loosely consolidated within the comet, bind together by the volatile ices. Right, let us say, like I told you, that you have let us say, water or other volatiles, and you put together some, very small amount of rocky powder in that, and you loosely consolidate it, right? Solidify that, and you start to heat it. So both would be lost. The volatiles that are present in the rocky portion and the dust portion, and the volatiles that are present, as the organics that are forming the ices. So that is how the differentiation between, the sodium or potassium tails and the tails of gaseous material, basically water rich, ammonia rich material. So that is how we differentiate between these. So we get the spectra of these, and on that basis the composition is constructed. So this is just to illustrate that a comet is made up of, different components, the gaseous component and also a small amount of dust component. And that is also selectively lost. That elements, if there are other elements apart from, just sodium, potassium, sulfur, right, elements like calcium, aluminium, magnesium, so they are still retained within these bodies, even once the entire cometary activity are done, because these are very refractory, very high melting point, elements.
Okay, thank you, sir. So it's basically you have shown it for illustration
For
in
illustration, to show that,
if
there are two different components. The gaseous component made up of volatiles, and there's another volatile component but consisting of rocky material or dust material.
yes, sir. Thank you.
Right. So I'll send you the glossary today, and then from next week we'll resume our regular classes Tuesday and Thursdays. Okay. And this is just a request that sometimes, like today, it was very nice. Some of you, responded, we interacted. So that was good. Let's try to do it this way. So that was the deal in the beginning, wasn't it? Okay, then I'll stop over here and we'll meet on Tuesday.